Okay, thank you. So actually, this talk will be resonating a bit with what Ben was talking at the beginning of his talk about the statistical physics intuition and principle you can use to build new algorithm, new sampling algorithm. And so my aim for this talk is to give you a nice story, like nice statistical mechanics speaking story about why PDMP or could be efficient and are actually efficient with sampling. Okay, so this would be somewhat not a very technical talk, and so sometimes if I'm not clear, you can just interrupt me. I don't know if it will work. But anyway, so the goal is to give you some insight on that. So I'll be reviewing some past work with different collaborators. So Sebastian Kapfer and Werner Kraut for particle works. The polymers will be with Tobias Kampmann and Jan Kirchfeld. And the Bayesian work was done with Alain Durmus and Stefan Seneca. Okay, so I will first start with non-reversibility. So why people are aiming to do that in Markov chain? So in order to be correct, to have a correct sampling, the only things, the sufficient things to do is to have data balance. And so to have this kind of balance, okay? So it would be like if you want to sample from these five states and you're in state A, you need to have between any pair of states a perfect balance of your probability flows. But actually, it's the only necessary condition is a global balance. And this would be to have a global balance between your inflows, so here, and your outflows, so here and here. And so the question is why people have been doing detailed balance when actually the efficient things to do would be to do maximal balance. And by that meaning that you only have the bare minimum flows to have balance. And actually it's because it has been quite easy to deliver schemes that are following this data balance condition and this symmetry condition. Whereas if you go to some global balance schemes, you need to find some global symmetry to have a general recipe to build these flows. And so the question that I will be reviewing is how one can find this global symmetry so that when they start in a point, they can go in a persistent way across the probability distribution and then change the direction according to this new information. Okay. So, oops. Oh, that's what I wanted to say. Local symmetry versus global symmetry. And so first I will try to convince you that actually the search, this hunt for symmetries has been an underlying principle of much of the algorithm of the sampling algorithmic development. So, oops. So if we start with data balance, one of the most known schemes, it's the Metropolis Hastings algorithm, or Hastings Metropolis algorithm. I don't know which one comes first, it depends on people. Which in physics, because I will be going straight into that, will be just given according to the energy change between your two states, as your probability will be your Boltzmann distribution. And it will depend on the energy of your state, and then here on the temperature parameters. And this data balance can be understood as if there is a way in, there is a way back. So meaning that if you have your state X and your state X prime, if there is a way into the state X prime, then do you have a way back to the state X, okay? And this can be seen directly on the rates where if you have symmetric proposal probabilities, which are this alpha over there, then if they are symmetric, so you can see here, if they are symmetric, then you have the correctness with this rate, okay? And so the question is, how can we do that? How can we see this symmetric thing in global balance. So first, something interesting that actually global balance can be understood as a continuity equation in physics, meaning that you have this integral balance, which is linked to the differential equation of the master equation. And the difference between data balance and global balance will be that data balance in reversible schemes is if there is a way in, there is a way back. Whereas global balance would be if there is a way in, there is a way out. So meaning that you're in X. Oops, sorry, this is not. You're in X. If there is a way in X, then there is a way out. And so this is different from the picture of going back and forth of data balance. Okay. And so it is very nice to think about this algorithm in terms of probability flows. So the probability flows will be your probability weight times the probability transition to go from this state to another one. And it can be understood in physics as some kind of mass times the velocities at this point. And global balance, with this continuity equation, it's actually the same condition as an incompressibility equation on these flows. And this gives you access to all the fluid mechanics type of ideas. Okay, so that's some other analogy. So, okay, so now the question is how can we do these subbalances of types in and out to have some kind of global general recipe to build these non-reversible schemes. So at first, data balance was, I mean, it was seen as a rule that one could not break. And so, for instance, for spin algorithm, for spin system, so here in blue, you have spins that are up, and in red, you have spins that are, for example, here, that are down. The idea was to find a way to do some correlated move across these clusters of same spin value. And the idea was to pick a spin. So for instance, this one, to pick a spin, to flip it, and then to build to build a cluster of spins that would be also flipped according to this first flip spin. And so it was very efficient because for physical reasons, it would percolate across cluster of same space value, and it would make persistent move across the probability distributions of the spin systems. But the thing is here is that this was a data balance spin, and this data balance schemes, and because the symmetric a priori probabilities were making it correct, meaning that if you spin if you flip a spin, sorry, if you spin a cluster, then the probability to flip it back would be the same. And that's what was making this algorithm correct. And so this algorithm started a hunt for this type of schemes that would be able to do some global move. And the point was actually to find this type of symmetric relationship. And so the goal was to make it available for continuous particle system. But in continuous particle system, you don't have this symmetric of flipping a spin, of this involuntary operation that if you have a spin up and you flip it, it's down, and then if you flip it again, it's up. Because here you don't have this kind of lattice symmetric. And so the idea here was to find back an involuntary operation in a continuous state space. And so if the pivot algorithm managed to do that by just throwing a random pivot in your system, and then flip. So here it will be reflect across this point the particle. Here you can see it here where you have the cluster of flip particles and the initial one, and then depending on the overlap, you will choose or not a cluster. And this was also very efficient in some type of system, but it is a very specific algorithm, and very quickly if you're in dense system, or for instance just a typical art sphere model, it will not be so efficient because you'll be spending your time making moves that are actually rejected. But this was again the idea that you need to find some kind of symmetry in your proposal to have a correct algorithm and an efficient one. If you look at Hamiltonian Monte Carlo, it's also a bit the same thing. So the molecular dynamics that was done first by Adler and Wainwright in the 50s was the idea to discretize the Newtonian dynamics. And then if you want to make it into a correct sampling algorithm, you just had a metropolis step to account for the non-conservation of the energy that is introduced by the leapfrog integrations. And actually, what is making this algorithm correct, it's the reversibility of the Newtonian dynamics and of this leapfrog integration. And, oops, sorry. Okay, and here again, we are down to symmetric alphas, which are the basis of the correctness of the algorithm. And again, this is artificially introduced. There is, no reason to have this type of symmetries there. So now the question is, okay, so historically, people have been chasing for symmetric alpha, efficient one, to do data balance. Now the question is, can we find some global symmetry to actually ensure directly global balance, okay? And so the key ideas here is that, okay, if we want maximal global balance, we want to cancel any rejection, which would be to replace any rejection by direction change, okay? And we'll be doing that by finding general symmetries to build these flows. And the key idea we have here will be to add persistency through lifting, which is actually the same idea that in HMC. And then we actually will be spending our efforts into extracting these real symmetries. And this will be done by factorizing, if possible, the interaction. And so going from a global probability transition into a product of independent ones. And then to add continuous time in order to also gain the symmetry of going up to the point of rejection, okay? So let me start with lifting and the idea of skew data balance. So lifting was first introduced by in the paper of Diaconis and al. In 2000, but it's HMC can be understood also as a lifting algorithm. So it's not something, it's not a new idea. The idea is that, okay, if you want to build persistency, you need to, in order to keep the process Markovian, you need to go from a space where with just your state to a state space where you encode both your states and the lifting variable, so here, which can, so in PDMP to be the velocities. And so you can understand the lifting can be understood that here you have your state space where, for instance, here you can go on the left, on the right with the same probabilities, or you can stay where you are, and you lift it into two replicas where in the upper replica you go always on your right, and in the down replica you go always on your left, and then you switch from one replica to the other to ensure balance. Okay, and this lifting variable E, its role is to fix your probability alpha. Okay, you propose a probability to propose the next state. Most of the schemes are making are made correct by fulfilling what we call skew detail balance. So skew detail balance is that, so here if I zoom in into just a pair of two states, is that instead of having a data balance between the state I and J, I will have a skew data balance between the state I and J, but in both replica, okay? And so here you can see that the rejection flow that I had are now transformed into a direction change, meaning that I'm updating my lifting variable. So on the existing state space, I now have a rejection-free algorithm, and I'm using the information of the rejection compared to previous algorithm where when you have a rejection, you just be throwing away your computation time. And no zeta balance can be understood actually as a lifted balance where in 2U state, you need to have a compensation of what we call the physical flows. So what is really happening inside the one replica plus the lifting flows. So that's the flow coming from the other replicas. Okay. So that was the ideas that was used in lifting in the Diaconis paper. And so what happens with particle system? So in particle system, let's say here I just have a system with two spheres. So I'll be moving this one, updating it. And when I have a rejection, then I will move it back, okay? And so if I look in terms of energy, so when I have a rejection here, it's like I'm moving in with a certain, I propose a state with a certain change in energy. And if I'm rejected, then I will be going back. And so here I will have a skew data balance in terms of energy between my proposition of increasing the energy and the decrease I will have if I go back if I'm rejected. The thing is here that in physics, with this type of potential, we have a symmetry there between moving a white sphere away or here moving the blue sphere away. And so using the symmetry, we can upgrade the scheme into a scheme where I'm not going backwards if I'm rejected, but I will move the other sphere. This may seem a bit trivial, but actually, this is a way to also break the skew data balance and to encode persistent move particles. And this was done by using symmetry encoded directly in the probability distribution and not artificially one like the Newtonian dynamics, some reversibility in time, and so on. And so the question now is, okay, but this is for two particles. How can we do that if we have more interaction term, if our energy is the sum of term? And the idea here is to go at the symmetry by factorizing the distribution and factorizing the probability transition. And so to take the metropolis rates and to take out the product. So we end up with a product of independent probabilities. And so instead of having these global pictures where it's hard to tell what's going on, now we have these clear pictures of symmetric interaction. Okay? This would have a cost because the rejection rate will be higher. But because here, when we have a rejection, we are just pushing the other sphere away. It's not a problem. Okay? Now, another question is that actually, if you just keep on having small discrete steps in elliptic schemes and you keep updating your sphere, like as this way, actually you won't have symmetric probabilities, a priori probabilities, because you will end up with with multiple collision. And so if you end up there, actually, if you just choose to move one, you won't be correct because the probability to go back won't be the same as the probability to have this multiple collision. And so that's why the continuous time implementation was proposed. And this is, and therefore people ended up with PDMP. And if you do PDMP, so you end up, if you look at your probability transition, then you end up with Poisson process, okay? It's very easy to see here the compensation of the physical flow and the lifting flow. And here you end up with your your Poisson process. And so here you have upgraded from this type of pictures of also this black box where you propose to have moved from one state to the other and you accept or not based on the global energy change, to this type of pictures where if you go from point A to point B, you see all your potential, okay? And so also the work has been done on how to explore this type of information, actually, like for pressure computation and so on. Okay, so let me wrap this up. So here, what I wanted to say is that, okay, people have been using local symmetry and reversibility to have metropolis type scheme and correctness, okay? And correctness was made through rejection, okay? In order to update it to a global balance scheme, we needed to upgrade this local symmetry into a global one. And here, we are not there yet. It's still like some kind of very strict symmetry, okay? And it is using, I mean, specific to potential that have this kind of mirror symmetry. But we have some tools. We have the lifting, we have the factorization, and we have this continuous tap implementation. And then this will give rise to the PDMP and all the analysis that has been going on since a few years on that. And also the question is to how to upgrade from the mirror symmetry to more global one and to more general potential. And so this is what has been going on since a few years. So for instance, take these polymers, okay? The problem is with polymers is that they have n-body interaction. They don't have mirror symmetry anymore, meaning that if you look here, you have a potential based on the angle. And so if you move the particle to here, you could have a rejection from both these two through the n-body interaction. And the question is how to pick the next one to move, this one or this one. And the idea here is that, okay, we don't have mirror symmetry, but we still have translational invariance, meaning that if you move all the particles, then you don't have move at all anymore. And this translational invariance tell you have a balance between moving all the particle in the plus direction and moving all the particle in the minus direction. And because of that, you can show that you can have a compensation between your physical and lifting flow if the lifting flow is respecting this balance. And this is again the idea that your global balance, meaning that in flow equal out, can be can be subdivided into subbalances of in and out flows. And so finding symmetry means finding this kind of subbalances, okay? So here we've been using translational invariance. So it works for any n-body interaction. And so the next question is, what if we don't have translational invariance? Meaning we have some kind of potential, for instance here, and we have a particle moving in it. And this is typically what has been going on with Bayesian inference. Oops. So in Bayesian inference, most of the time you have some prior distribution that acts like an external potential. And so the idea of people there has been, again, to enforce some kind of artificial a priori probabilities. So artificially symmetrical one, meaning that if you go up here, in order to have this balance, you will propose a move that will have the same decrease in energy as the increase in energy you were proposing. And so one thing that would have been correct would be to go back, but it's more interesting to reflect your direction. And so you'll be using this mirror symmetry again by reflecting across the boundaries of your distribution. The problem is that by doing that, you're enforcing artificial symmetry, and this is actually quite a constraint, because by doing that, you need to add lots of randomness to be ergodic. Okay. And the problem is that by adding this additional randomness, it's really hard to tune, because it's like HMC. If you put too much, then you have a diffusive dynamics again, and you'll be losing lots of efficiency. But actually, if you look at these pictures, there is no need to enforce this type of artificial symmetry, because this balance, it's actually part of a much global balance, which is the global rotational symmetry around the gradient. And so, oops, sorry. So if you look at any possible vectors in, so where you go up to potential, you have a balance with vectors going out. And because you have this balance, this is the balance we'll be using to have correctness and the global balance in the non-reversible scheme we are aiming for. And so what we'll be doing is that instead of having this reflective type dynamics, it's as that at each point where you need to change direction, you'll be picking a different angle, okay? And here you will have stochasticity that will be introduced again, but here this will be using directly gradient information, and actually this will be picking out an angle based on this distribution, okay? So this is not the same as adding artificial randomness. So for instance, I'm picking a vector following a Gaussian distribution, or uniformly on the sphere, okay? So I don't know how much time I have left. I should have some more.
Yeah, you can talk for 5 more minutes if that's okay.
Perfect. So yeah. So I will just show you some movies. So here I have a simple Gaussian distribution, and it's just to show that here. So I have a scheme with reflected scheme. So actually, that's what is known as the BPS of Bouchard, Follmer, and the Doucet. So Bouncy particle sampler. This one also. So I'm just bothing around my distribution. Here is when I add some randomness, okay, in order to be ergodic. And here is where actually I don't put any randomness, but when I have an event, I'm picking a new direction based on this global rotational balance around the gradient, okay? And oops.
I'm sorry.
No, it's not working. It's not working, but that's okay. I will.
Okay.
Perhaps I can share my screen there.
Oh,
Okay, just wait. No, I have the solution. I have the solution.
Okay.
Up. Okay. 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 This should be working, right? Okay.
I can see a screen, but not yet the video.
Yeah, I think there's just a delay.
No, it's working.
Yeah. And so here it just to show you that you have a problem of ergodicity when you have just the reflection. But really the point I want to make across is that if you're making your algorithm correct by enforcing very artificial constraint, then you pay the price, okay? And here you can see that if you add randomness, it is very easy to change a ballistic schemes into a random walk type of dynamics, okay? And here on the right, you see that actually if you're not making any constraint and just using some global symmetry that actually you have for any potential, you can be much more efficient and you can conserve this ballistic type of trajectory. And this is most interesting when you have, so let me just, okay. When you have, like here, a very cigar-shaped distribution where here, so it's just a Gaussian distribution, but my variance comes from 1 to 10 to the 6, okay, to 1 million. And so here, it's just a nice test case when you want to test the ability of your algorithm to separate dimension and to stop the pollution from small dimension here to high dimension. So high dimension meaning that where you have a very big variance and you just need to keep going on this dimension to see the full variance. And here, so I would show you a little movie where here you have the metropolis on the left. This is a section of the last 2 dimensions, so the one with the biggest variance. And so the problem with reversible algorithm with lots of randomness here is that you'll be stuck in the middle because each time you propose a move, you have a non-zero component on one of the small variance dimension, and so you will reject the move. And here will be HMC and a PDMP with reflection type direction change. And you see here that if you look at small dimension, it will be ballistic, but if you look at the large dimension, it will look like a random walk diffusion. And here in the last one will be when we enforce the global symmetry and we pick a different direction based on the gradient direction. And so by doing that, we just need to enforce a 2-dimensional noise in order to be ergodic, to switch from plane to plane. Whereas if you do just reflection, you need to have an n-dimensional noise to be ergodic. Okay, so just the movie show that, and then it be done. Okay, just it started already. And so here it's to show that breaking any artificial constraint that has been put here just to have correctness and looking directly at the global symmetry in your problem and using them to enforce the global balance is helping you out to be efficient. Okay, so here I go back. Okay. But this is not the end of the story there, because the point is here, even with this global rotational symmetry and this stochastic direction peak at each Poisson event, there is still a 2-dimensional noise that needs to be added. Okay, and so the question is now is there a way to avoid doing that altogether? And this would be, I mean, an optimal algorithm to do. So, okay, I will be wrapping it up here. So I try. It's not really on Zoom, and also I'm not really at my office, so it's a bit not so comfortable to do that here. But I really want to give you the idea of finding global symmetry, stopping artificial constraint. I couldn't talk about how it can be used also to use to reduce the complexity of the computational complexity of your algorithm. But there's also the idea, because the point is that if you're using symmetry of your distribution, the symmetry of the distribution is like actually using some kind of dimensional reduction, because if you have symmetry and you use them, or you can factorize and so on, it actually means that your distribution is simpler than what you think it is. And so everything here is linked in these pictures. So PDMP, so perhaps it would be more like one of the following talks, but so they are quite interesting. They have all these nice ideas of going straight for the symmetries of the distribution instead of using artificial one like the reversibility, but there is a cost. So they are not so well understood, theoretically speaking. They are quite hard to analyze, actually. And I didn't have the time to talk about the difficulty of the implementation, because computing the exact event point can be difficult outside of statistical physics, where we have all these nice symmetries, and this is not really a problem to find that. But in general, Bayesian inference, there is this problem. Okay, so I think I should end it here. And so thank you very much for your time and your attention. Very early this morning. Yeah. Okay.
Thank you very much, Manon, for the interesting talk. Any questions?
Yes, maybe. So again, it's me, Pierre. Hello, Manon. Thank you for the talk. In the simulation that you showed us, so the behavior of the bouncy particle sampler was really noisy, like you said, similar to random walk. But wasn't it related to the choice of your refreshment rate? And for instance, and you took the example of the when you have 400 dimensions, some with very high variance and low variance. And so I'm not a defender of any particular algorithm, but I believe one could say, okay, you just have to precondition as everybody does, and then you would have, when you refresh, you don't refresh. So either you don't refresh with the same variance, or you don't refresh at the same rate, like related to the talk of Benedict M. Kuller with different well, learning rates for different. So I mean, I don't know if it's really related to picking a new velocity or bouncing, or the problem is more the refreshment, the kind of refreshment that you are putting. And so my question is, when you do the simulations, have you optimized the refreshment rate for the bouncy particle sampler, or have you just put one and just to?
I just try to kill the algorithm.
No, not to kill, but not.
No. Yeah.
Because
okay.
even
Thank you
small
for the
dimension
question.
is very close to random walk. I mean, and I understand for the large dimensional. Okay, I'm pretty sure even if you optimize, you get that. But
yeah. Okay, so the algorithm here was really optimized. Like really, I really tried to optimize it, and so there's different dimension in your question, so the different dimension in your answer. So here's the noise. The noise was just picking a vector on the hypersphere, okay, of the Gaussian. The rate of the refreshment was optimized so that the algorithm will be the most efficient. Okay, so everything, I mean, like I put everything in the papers. I put like actually like in the appendix, I put like all the different results depending on the refreshment rate, so people can be convinced on that. So here for hypersphere picking, here it's optimized. But the thing is that if you want, if you look at the decorrelation, if you look at the position, okay, your x, your vectors, then actually your bouncy sampler will want you to put like no refreshment rates, because if you do that, it will be going around, and because x is a vector, then it will go to 0 very quickly. Okay, but if you look at the norm or at the potential, so like the sum, you do your Gaussian with a state, then the problem is that if you do that, you'll just be going into circles, and then you won't be decorating into actually your norm or your energy. So that's what I was looking at when I was trying to optimize this algorithm, because actually the hard thing to decorrelate for this type of algorithm is not to go around. They are very good to do that, but it's to go around and then to go across also, and to see all these different levels. So everything here in the paper. So what I've tried also is that, okay, I will keep the bouncing scheme, but I will put the same noise as I put in the one with the stochastic direction, okay, not the reflective direction peak. And when you do that, the algorithm does, I mean, perhaps it is ergodic if you can prove it is ergodic in the long run, but when you do simulation, it's very hard for it to quit the same energy level because there is not enough noise there. Also, something I have tried is to put the stochastic direction change, but I've put the same noise as for the reflective, the BPS scheme. So n-dimensional sphere, hypersphere peak, okay? And the point is that, so actually, if you do it with the same rate as for the optimized BPS, it will be faster to decorrelate the energy at first. And then it will find a very slow time scales as a BPS. But you have first a fast drop in the decorrelation. But then because you have this stochastic direction peak, you can actually turn down the rate of the refreshment and have an efficient scheme. And so what I want to say is that actually there is, like, if let's say you have efficient BPS, let's say you have an efficient BPS, actually you can take this efficient BPS and just plugging a stochastic direction peak, and it cannot be slower, because adding the direction peak is not adding randomness, because you are picking a vector directly according to your final distribution. It's a direct pick, actually. So you're not adding randomness, you're directly sampling your stationary distribution. And so the whole point is that why spending your time optimizing an algorithm, artificial random refreshment, when you have a direct stochastic refreshment that is directly following your distribution. So here the algorithm were optimized. But no, so sometimes I have a question on HMC, because the HMC here it's also optimized to have following some adaptive scheme. But naturally here it's a Gaussian distribution, and with a Gaussian, you can do some adaptive trick in order to find your eigenvectors, to find the direction, so you can actually factorize your Gaussian. And here I didn't do that for any of the schemes, because actually if you can do that, then the most efficient things to do is just to do a plus and minus type of algorithm on any of these dimensions you have factorized your Gaussian into. So this is one of the questions also I have on the, okay, did you kill or not the HMC for this movie? And here I'm not using any adaptive trick. I'm just using, okay, what if you look at the dynamics, what the algorithm are going to do without any information on how the matrix, I mean, on how the Gaussian is shaped.
Okay,